Yes, we start the new year. Today, gentlemen, please. Probability 3 for normal distribution. So what we're going to do today is I'm going to introduce the standard normal distribution. Look at standardising the curve and the normal standard variate Z, and then determine probability from a normal distribution and look at the problems involving the normal distribution. So, introduction to the standard normal distribution. The curve of a normal distribution is like that shown in the diagram of figure 1. It's an extremely important one and can be expected to be produced when a data sample is large. So you've got a lot of data in your sample, you'd expect quite often to get what's called the normal distribution if you plot that data. This curve can be described by a mathematical equation and the basis of much of the work in advanced statistics. Many natural occurrences, such as the heights and weights of a group of people, expect of people distributed about a mean, the sizes of components produced by a machine, so there's a standard size of component with variation around that, the tolerance of that, you expect a normal distribution, and the life length of some components you would. Alright, so that's what it is. Normal distribution curves can differ from one another in 4 ways. By having different mean values, by having different values of standard deviation. We've already looked at standard deviation. That's a standard amount of variance from that mean across your set of data. Okay, that should read the variables having different values and different units, and by having different areas between the curve and the horizontal axis, which we're coming on to shortly. Okay, so what does all this mean then? Standardising the curve. What they do is standardise the curve and look at, and there's what's called a normal standard variate Z. The mean value of the unstandardised curve is made the origin. So what I do is to make the mean value in the middle, or the peak, where the peak of, try not to say the middle because they can skew one side or the other sometimes. Okay, the mean value is the value up the middle. Okay, then everything to the left are values in your data that's less than the mean, and everything to the right is values in your data that are greater than the mean. And as you get further and further away from that mean, you get less and less data with that value. Okay, so we actually set the mean, that's x bar, equal to 0. And that's what we do. So this value in the middle there is equal to 0 in terms of the probability. The horizontal axis is called standard deviations from that mean. This is done by letting the Z value equal the value that you're analysing. So if our mean is 1.5 metres tall, and we're looking for the probability that someone will be 1.4 metres tall, then the value x is 1.4. We take away the mean value and we divide by the standard deviation. We get the Z value, which is the normal standard variate. Okay, and this will all become much more clearer actually when we look at an example. Alright, and then they say that the area between the normal curve and the horizontal axis, that's shaded in red, is equal to 1. Remember, 1 is always the sum of all your probabilities. Do you remember that from before Christmas? So if we've got a number of different actions, all with different probabilities, if we add them all together, they should add up to 1. So the standardized normal curve, we say that the area beneath it is equal to 1. Yeah, because that would cover every sample in your data then. That will add up to 1. Everybody okay with that so far? Bear in mind at the moment that's still quite abstract in terms of we don't know how we would use it. Okay? So, next slide. Determining probability from the normal distribution. So once you've standardized the normal distribution, it's called a standardized normal curve or a normal probability curve. And any normal normally distributed data can be represented by the same normal curve. The area under part of the normally distributed probability curve is directly proportional to the probability. The value of the shaded area shown in the figure below can be determined from that formula there, which you aren't going to do at this stage. Okay, we are studying calculus, so that's finding an integral, that's what that slide means. We're studying calculus after the second half of the module in February. Okay, and you'll see why you aren't needing to do that in a minute. So what you would have to do is whatever values area you're trying to find, you'd have to do that calculation over and over again. And what's been done, in order to save repeatedly determine the values of that function, tables of partial area are included in many mathematical formula books, and such a table is included on the next page. So on that page we've got a table of the areas for given z values. So once you find your z value, let's say you find a z value of 1.46, here's 1.4, then we go across to 6, and the probability of that value 1.4, 1.4 standard deviations from the mean is 0.4279. So you just go to a table of z values and find your probability from the table. Okay? So we find our value of z, that's how many standard deviations it is from the mean in the middle, and then you come to this table, like I say, z value of 1.46, we come across to here, and we've got a probability of 0.4279. Yeah. Okay. And as you'll see shortly, if you've got that, and there's your 0 part there, and you want to find the probability between two z values, z1 and z2, that data, what you'll do is that z value, find that area there using the first z value and add them together. Yeah, that gives you the overall probability of your data being accurate. Alright, so that might be heights between 1.4 and 1.6 meters if the mean is 1.5, for instance. Okay, so you're going to be using that table, and if you are asked to do anything like this in assignment, the appropriate table will be provided for you. Alright, you have calculus. So let's have a look at a problem. The mean height of 500 people It's 170 centimeters. So X bar is 170 centimeters. And the standard deviation is 9 centimeters. So that's simple as standard deviation. Yep. I'm assuming that these heights. So we're assuming we've got a curve that heights like so, where this is 170 centimeters, and we've got left middle one standard deviation of 9 centimeters. Determine the number of people likely to have heights between 150, so 150 is over here somewhere, and 195 is up this end. So we call that Z1, and that's Z2. What we need to do is find probability is equal to Z1 probability plus Z2 probability. That will be the overall probability of it. So Z1 is equal to the value at Z1, 150, minus the mean, 170, over the standard deviation. Calculate that. Z2 is 195 minus 170 over 9 equals. Minus 6.0, give me 2 decimal places. 2, yeah. And this is plus 6. Okay. So the negative sign means that it's to the left of the mean, and the positive sign means to the right. So you need to go to your table and find the Z value for, or the probability for Z1 and the probability for Z2, which are actually the same. So you go to your table, you're looking for 2 point, yes, hang on, Toby, how do you get the same value? Not the same value. Where's 195? This is 195. This one, not 40 you calculated to? 2.77. So you have got two different values of probability. So look up the table, find the probabilities for Z1 and Z2. What we've done here is found two Z values, Z1 for the area left of the mean, and Z2 for the area right of the mean. We've then used the table to find the two probabilities, the left hand side and right hand side, and added them together to get the overall area under the curve. That is equal to the probability of it being between those two Z values. Okay, and then we multiply that overall probability by the sample size to get 492 people. Please remember that you would expect, or else the number of people that would likely be between those two values. But that's what the normal distribution of probability says it's likely to have to be the case. Right? Yeah, and the reason they've got 2.7, the reason why I said it was 0.4973 is actually, if you rounded correctly, I think you'll find that's 2.78. 195 minus 170 over 9, I think that rounds to 2.78. You need to be careful with your roundings. Right. Step 2, let's have a look at it. For a group of people, given in problem 1, find the number of people likely to have heights of less than 165 centimeters. So we've got our normal distribution we had before. This is 170 centimeters. Standard deviation is still 9. Remember? Okay. But what we're saying here is there's the middle. There's 165. We want the area in here to the left of that. How are we going to find that? Or how are you going to find that? What are you going to do? What area are you going to find to take away from that? Yeah, but you don't. What you can't. What's the area of half of this? What's the area of all of that? If the whole thing is 1. But the area of half is 0.5. Yeah. So if you find this this area in here, take it off 0.5, find that probability in there, take it away from 0.5. There we go. Gents, this Z value, we must have 3 digits and we must round it correctly to 3 digits. because that's what the table needs, including the 0 in front of the decimal point if that's necessary. Yeah. So the value here comes out at 0.55 reoccurring. We need to make sure we round that to minus 0.56. Yeah, but you should round it. You should round it to 3 digits. Where you were the answer in this one, Z value should have been 2.7 for the second one, 2.78, because that was 2.77 recurring, so you should have rounded it to 8. Okay. You must do correctly rounded to 3 digits, including a leading 0 if necessary. Alright, so we want the Z value, therefore we can say the area for 165 centimetres equals, and we go to the table, we're looking for 0.56, there's 0.5, there's 6, 0.2123. Check I've got that right, yeah. So that's the probability it's going to be 165 centimetres. We're interested in people to the left of that. Because the normal distribution is symmetrical around that mean, yeah, that side is the same shape as the left hand side is the same shape as the right. The area of the whole is 1, therefore the area of half of it, everything to the left, is 0.5. So we can now say minus 7. Therefore, expected number of people is 0.2877 would have been unimportant. Okay. Just multiply the probability by the sample size to estimate how many people you would expect the Right. So, problem the same group of people given in problem 1, find out how many people are likely to have heights of more than 194 centimetres. So this time we're on the other side. There's our 170. There's a normal distribution. We want to know how many here 1947. For this problem, Z is 194 minus 179. It's 2.67 standard deviations. Yeah. From table, probability equals 0.4962. Therefore, probability of more than 194 0.5 minus 0.4962 is 0.038. Yeah, so that's the probability of someone being over 0.194 centimetres. Therefore, expected over 194 centimetres equals 0.0038 times 500 equals 2 people, rounded to a whole person. Okay. The next problem, it looks like I've missed it out. 1,500 lemonade bottles have an average content of 750 ml, so you need 750 ml, and is 1.8 ml. If the volume distributed, find I number of bottles with less than 750 ml contents. B, expected number of bottles. Between one 4 ml C more than 757 D Yep. That's 751, that is.
There you go. Last one, part D. Number of bottles with contents between 750 and 751. That last bit, what you should notice is that you're already calculating the value of 750, so you've got to do 75.